Okay, and I'll share my screen as well. Okay, so maybe before going ahead, I'll quickly summarize what we had done in the last class. So in the last class, we started to look at the Titanic dataset, and the whole idea of exploring this dataset is that we learn how we can implement methods of data pre-processing, which we studied a class before, which included data cleaning, integration, reduction, discretization, smoothing, and so on. And we thought we will take those concepts and try to apply those concepts on a good data set. Titanic data set is a fairly uh, exhaustive data set. It's not very hard, but it at least exposes us to the problems that we may face in other projects. And we'll try to, in the first part, we'll try to at least do pre-processing and feature engineering. And once we have done that, we will take a break from the Titanic dataset. We will further explore machine learning and then come back at Titanic. Okay, so that was our a little backdrop on which we are working. The Titanic dataset is basically, let me show you, is data like this, where we have our features as passenger ID, survived, passenger class, name, sex, age, sibling, spouse, parent, children, ticket, fare, cabin, and embarked. Okay, of which we had explored, we had done some descriptive analytics, basic analytics on this to find out how many data points are there, how many missing values are there. We saw it for the train set and for the test set. Going ahead, we saw how many missing values are there in both cases. And we defined a function bar chart that will help us give these kind of bar charts, which will give two bars, one for survived and one for dead. And in each bar, there will be multiple stacked bars for the different categorical features available for different categories or different value counts available within that categorical feature. So we saw for gender, we saw for passenger class, we saw for sibling spouse, parent children, embarked, and probably that is where we stopped last time. And we said we will start with feature engineering here, where feature engineering is basically the process of using domain knowledge of the data to create features or feature vectors that will make machine learning algorithms work. Okay, so it is basically taking this data and filtering out and combining different features together and making it a bit easier for the algorithm to learn patterns out of this data set. Okay, so do you have any questions before we start? Okay, did you get a chance to explore through this notebook earlier?
This dataset, no.
Okay, okay. Anyways, for later access, we have like I have put this up in here.
Yeah.
So you can download the zip, open it up, and you can go through the material within this notebook. So it will be an interesting exercise. Okay. Anyways, let's go ahead. Yes. So now what we'll do is one by one we'll start breaking down the different features and see how we can convert those features or what we can do with those features so that our machine learning models can become simpler. The first feature we'll look at is name. Okay, so from name, do you think we can do something interesting with name here so that our models can become better? Or maybe that's a very complex question. Let me ask a simpler question.
We can avoid names.
Okay, yes, you can avoid names. Okay, and what is the logic behind avoiding names?
Name won't matter, and we can't keep text to the final dataset.
Excellent.
Digital.
Excellent. So both of ideas are good. Name may not matter while deciding someone survived or not. Uh, and the second thing is we cannot feed strings to our model, or even if we have to feed strings, we have to either convert them into some numerical format which makes sense, and that numerical format we can we can use. But interestingly, there is, even with this limitation, we can still do something interesting with the names. Okay, so what I've done is, you see each of the name formats, it also has a title associated with it. Like for example, here we have Mr., we have Mrs., we have Miss, Mrs., Mr., Master, Mrs., and so on. Okay, so even within the name, probably this title may have some correlation with the survived or not. How? This title has definitely has correlation with the gender, and along with the gender, this title has some correlation with the sense of uh, age as well, because we've got master and miss, which represents probably male and female of lesser age. Okay, of or master generally is a title which people don't use nowadays a lot, but uh, I knew in my school days my, I would attach master in front of my name, saying that, representing that I'm a small boy or something like that. Miss in front of someone's name, informing that it's a small girl or something. We also have titles like Doctor, Reverend, Colonel, Major, and so on, which represents the class of a person. Okay, class means what category the person works on. So there could be some value in extracting these titles out of a person's name, and then seeing if that title has something to do with gender or with age, or does it have some correlation. Does it make sense? Okay, have you at least got what I'm trying to put at this point? That maybe before discarding name altogether, we may first explore what the titles, how the titles are correlated, and then if we don't see any value, we can discard it altogether. But if we see some value, we can use this from the names page. Okay, so in this case, uh, do you know some methods that we could use to extract this title from a name, or what could be the strategy to extract titles from a name? Hmm. Any ideas? Are you saying something, Swetcha?
Yes, can we give some string comparison,
Mm-hmm.
some condition like that if string contains
Yes, yes, of course, we can try something like that. You said we can give some rules where we can take a string and from that string put some. So one option that you suggested is we, what did you say?
yes, if name contains that particular word
Okay.
that we want.
Yes, but the problem with that method is we should know all the possible combinations that people will be using, right?
Yes.
Hmm. So maybe a few common things that we can check for is Mr., Mrs., Miss, Master, and so on. But interestingly, if I go a little ahead, maybe let me check data till the first 100 points, and I explore this. It hides a lot of information. But since I've explored this data, I can tell you that there are titles like doctor, there are titles like major, colonel, and some titles that we are not familiar with, but they used during that time. So it would be difficult for us if we give a preset list, we may not capture uh, all the different titles that are there in the different names. Can you think of some rules that we can apply, and those rules will help us extract the names? Do you see a pattern in all of these names?
Uh, the initial comes after comma, so we can do something like
Okay,
that.
okay, excellent. So you have observed that all of these titles come after a comma. What next? There is also a space
Yeah, and a dot.
and a dot. Excellent. So we are already seeing some patterns here, right? And maybe we can use these patterns to extract something that is meaningful out of this. Okay. So if have any of you heard of something called as regular expressions? REGEX.
No.
Okay. So a regular expression is a way where we can define rules which helps us to match patterns. Okay. So, those patterns are, probably you must have used this sometime. If you want to search files on your system, uh, and you know some parts of the file, but you don't know other parts. Let's say your files are named as file underscore 01 underscore 02 underscore 03, and you want to capture all of these files. You could search for something like this: file underscore star dot txt or dot py, and what that star will act, the star will act as a wildcard, and your computer will search for all those names that follow this pattern. Okay. So in a similar way, regular expression also works that way. Okay. So regular expression, we can define certain rules. So in this case, the rules would be, or the rules I have defined would be something like this: wherever we have a space followed by a capital letter, followed by a series of small letters, and then ending with a full stop. Okay. And if I match this pattern, from that pattern I will extract the capital letter followed by a series of small letters. Okay. Now to do that, uh, we have the next part of the code. I realized that I have to do that over all the names within the train and test. So I said, okay, let me right now create a list of these data frames, train and test, call it train test data, and run it through a loop. The loop will apply on both these data sets. And I'm saying that for either of these data set, I'll create a new feature called as title. So within train, there'll be a new feature title. Within test, there will be a new feature title. And what will I fill in this title? Okay, so I will fill in this title anything that is returned by this line. Okay, so this line, what it does is it operates on the name feature, so dataset name, and then on this name feature, we call a function called as extract. So the name feature is a string, so I call modules that come from the string, so str dot extract, and my extraction pattern is given by this code, and expand is equal to false. Okay, I'll tell you what this is here. So this code is something that understands the pattern that I explained earlier. Okay, so this is something that comes under regular expression, regex. Now, it is not necessary to go back and learn what this is, but if you want to define a regex, you can simply search on Google regex. So there is a regex cheat sheet which gives you short formulas that says how we can use regex. Okay, so there are simple codes like if you want to take a number, if you want to take a character, and so on. Further, you can use regex tester kind of something, where you can experiment by adding some piece of code, and uh, testing by putting some piece of uh, regular expression to extract certain things. Okay, so there are many tools like this, so you may not have to actually go and study this in detail, but maybe spending half an hour on these tools can help you come to the script like this. So I'll explain to you this script. This script says whatever string that I'm interested in starts with a space. Okay, the parenthesis is what I'm interested. Okay, so after matching the string, whatever is there in the parentheses, I will get that as a return value. Okay, and within this parentheses, I am looking for a to z. So a capital letter followed by a small letter. The plus sign says that go till you finish the word, and the word ends with a dot, which I don't want in my name. Okay. So if you explore this little more, you'll get some more idea on how this is working. So now when we apply this on this string, it is able to extract these titles out for us. Okay. And when I further, after executing this, if I look at train.head, I can see that now I have a new column called as title, and this title has extracted these from this name. It has extracted these titles out. Okay. The next thing to do would be, okay, what are these titles? What are the different categories of titles? So we can always use, for categorical data, we can use value counts. So I say train title dot value counts, and it gives me all the different names that are available. Okay, all the different titles that are available. So you see, interestingly, people have used Mr., Miss, Mrs., Master, Doctor, Reverend, Major. MLLE is again some kind of military title. Colonel, Miss, Don, John Keel, Sir, Lady, Captain, Countess, MME, and so on. Okay. There are different titles available within the train dataset. There are different titles available within the test dataset. Okay. So our next task would be, so even though we have the title here, we have to, even if I have to feed this to the algorithm, I have to convert these to numbers, right? So I use a simple title map. I say, okay, for all the misters, we will use the code 0. For all the miss, we will use the code 1. For all misses, we'll use the code 2. For everyone else, we'll use the code others, okay? Depending on which are the major categories that are covered within this data. So once we have the title and we have arranged for a title map, the next would be to apply this title map on this code. So we could easily do a binary filter or something like that. But I could also use something like this. I can create a dictionary which defines the title mapping. So it says, okay, title mapping, Mr. 0, Miss 1, Mrs. 2. Okay, everything else. Okay, so everything else that is there within this list, I'll take that and say, apply the title 3. Okay, or let the title mapping be 3. Then for dataset within train test dataset, within train test data, that is apply for both the train and test. We're saying that wherever we find dataset title, we'll map it using title mapping. Okay, so and we'll populate again the same feature title. So once we do that, we see that now we have an extra column here, and that extra column shows numbers 0, 1, 2, and 3, 0, 1, 2, 3 for both the train and for the test. Okay. Now that they are in numerical format, we can further see correlation, or we can see how they are related. So if I take a bar chart on this title, the same thing that we had, the same function that we have created, we get this plot. Okay. So can you give me some inferences that we can pick from this plot? Let me just tell you. Okay, Mr. is 0, Miss and Mrs. are 2, others are 3.
1 and 2 survived more.
Yes, 1 and 2 survived more. That
Yeah.
is Miss and Mrs. survived more. And
Okay.
both the other categories, that is Mr. and others, were others is fairly equal in both cases. And Mr. is someone who suffered a lot. So time and again we're getting reinforcement on this. But at the same time, this title may contain some extra information which we do not know. So instead of just removing the names, we could find some correlation, some modified format of the name that we could use. Okay. Yes, so once we have extracted the title, the name is no longer important. So from both these data sets, train and test, we can drop name in axis 1 in place as true. So that is within the same data frame, it drops the name feature. Okay. Once we drop it, this is our reduced form of train and test. Okay. Do you have any questions within this part? Have you understood it? Okay, excellent. Let's go ahead. Then we look at the next thing, gender, sex, male or female. Same like we did mapping for title. We can do a mapping for male and female. So we are creating a dictionary called a sex mapping, saying that males will be interpreted as zeros, females will be interpreted as one. And for both these data sets, we'll call the map function to do this. And once we have done, let me actually run these two. Yeah, once we have done it, now we can also see gender. So earlier we could not see gender, right? Or no, we could see gender, but they were as names here, male and female. We have the same thing now with numbers, 0 and 1. The whole idea is that we can, these numbers can be fed to an algorithm, and that algorithm can do something with it. Okay, let's go ahead. Let's look at age. Okay, so now age, there are certain missing values. In train, there are 117 different missing values for age. Uh, Out of 891, 177 are missing. Okay, so some age is missing. Let's use title's median age for missing age. Okay, so maybe let me ask you the question. Out of the 177 missing values, how do we populate the missing values? Or do you have any ideas that we can use to populate the different missing values?
We can take the help of this title that we have just populated.
Mm-hmm.
See the tag whether it is Mr. or Misa,
Mm-hmm.
and then we can take the average of that particular. If suppose it is under category 1,
Right.
then we can take the mean value.
Yes, excellent. Good. Yes, yes, that is one interesting strategy that we can use. Okay, so let's say now we know different titles have different groups of people. We can use that information just as Switcha rightly pointed out. We can use that. Let's say if we did not have this, my default view would have been that take the mean age and using the mean age, assign that to every missing value. But now, since we have something extra that we know may correlate with the age of a person as well, that is title, we can use this extra information to fill the data. Okay. So here, a very simple strategy would be, let us group by title, and for that grouping by title, let's find the age and use median of that to get this number. So what does that mean? Okay. So let me probably try to break it down. So we say train group by title, and let's say just age. And before applying this, we can do a count on it. Okay. So what it says is, these are the different groups of titles: captain, colonel, countess, don, turnkey, and so on. Okay. And for these titles, these are the counts of people. So there are 36 master, 2 majors. Wait a second. Okay, I think I have, let me run this. So I think I skipped running that title mapping. Yeah, I'll run this title mapping. Yeah, let me go down again. Okay. Yes. So after running title mapping, we see that for class 0, there are 398 cases. For class 1, 146. For class 2, 108. For class 3, 62. So if at all there is a missing value, what we can do is, there are 398 misters available. We can find what is the median age here, what is the most common age, or what is the center age here, what is the center age here, what is the center age here, and here. And if someone's age is missing, we replace with this, the age of this median value here. Okay, so we have like maybe a generic something that is not too not too much disturbing our data, but at the same time satisfying our criteria of not having missing values. Okay, So when we execute that, so here we did it for count. Instead of count, if we do, let's say mean, we can see that the mean age of someone, of a mister, is 32.3. The mean age of a miss is 21. Mrs., is that it? Just verifying. Our mapping was Mr., Miss, Mrs., and others. Okay. So yes, Miss is 21, Mrs. is 35, and others is 20.4. Okay. That is our mean. If we do a median on this, so if I do transform, then for each case, we have these numbers 30, 35, 21, and so on. That is the most, the center value for that case. Now, once we have this data, what we would want to do is we would want to replace the missing values with this data. So here we say fill. So for train age, we say dot fill NA, that is fill the missing value, fill the null value with this thing. This is the thing that we calculated here, and in place is equal to true. So wherever we find missing values, we will populate those with this age. And probably this would be a better uh, guess of filling the missing value than the mean and the mean value that we have. Okay. So when we execute both of these terms, now we see that our model does not, our data does not have any missing values of age in the train and any missing values of test of age in the test data set. Okay. So let's go ahead. Next, I'm doing some more analysis. We are doing a KDE plot. So a KDE plot is basically the distribution plot, but instead of a histogram, we have a smooth curve, and we are doing it for age. Okay. So here I create a facet grid because I want two plots actually. I create a facet grid for train, and the hue is survived. That is, the color will be decided based on survived or not. Okay. And to this facet, we are mapping KDE plot, which is your kernel density estimation plot, for the feature age. Okay, and we are putting shade as true. I think shade as true has to do with the alpha component or the transparency component. Okay. After doing that, after running this, we should get this plot. We are adding a small criteria here to set the minimum and maximum age. So at this point, it is not important, but it will be important in the next part of the series. So here I'm saying that start the X limit from age 0 and end it at the max of the train age, okay, which is okay, right? Once we have that and we say add legend, we get this plot. Can you look at this plot and try to interpret some information from this plot? What information can we get from this plot? Or do you see something, some highlights or observations that can help our analysis?
Maybe the persons between the age 20 to 35 or 38 died more.
Yes, excellent. Very good observation. So here we have two plots, the one in blue and the one in orange. The one in blue is survived 0, that is the people who have not survived, and the one in orange is the people who have survived. And we can see that age does play a factor in someone who has survived or not, because we see that and since we have overlapped that, we can see cross sections, right? So if I put when these two lines cross somewhere near age 18 maybe, I can say from age 0 to age 18, most likely people have survived, because the orange curve, the orange uh, kernel density estimation plot is faring higher or has more frequency than the blue KDE. Okay, so within this range, people have survived more, died less. Within the next range, let's say from around 18 to 35, as Svecha pointed out, we can see that people have died more and survived less. And in the next age group, again from here onwards, we see probably till here, people have survived more, and maybe older people have not survived as much. Okay, and this plot gives us some more information. So let's say if I have data like this, 22. So let's say if I have data like this, 35 or 30. Okay, let's say 22 or 26. Okay, let's take these two samples, 22 or 26. Does it matter uh, having different values of 22 and 26, or it matters that they belong to this group of data? What has more sense?
It doesn't matter about individual values. We can take a group of values.
Yes, excellent. Okay. So we saw that probably this graph reveals to us that uh, groups of ages matter more than individual ages. So the variation within a group may not be as important, okay, or may not be as important. Plus, on the contrary, the variation within a group may actually act as noise to my model, because we now see that it does not play an important role here. So it is actually noise. So since it is noise, we'll go to the data cleaning step. Okay, and within data cleaning step, how do we deal with noisy data? So one option is you bin it down, or do a process called as binning. Uh, Take groups and smooth out the data. So in this case, that is my plan. That looking at this, I would smooth out the data. So I'm just uh, changing the X limit criteria to see different zoomed out versions of the plots, so that we can identify these intersection points. Okay. So I do it for 0 to 20 to find the intersection point, 20 to 30 to see how things are working out, 30 to 40, 40 to 60, and so on. And after going through the different sections of this plot, I probably figured out that let me divide this age criteria into 1, 2, 3, 4, 5 different categories. Okay, child, young, adult, middle age, and senior. So you could have gone. So again, this is a preference option. You could have gone with lesser classes, or you could have gone with a bit more classes. But the idea is, instead of having age as a continuous feature, we can have age as a discrete groups of events. Okay. So this mapping I finally associated with this range, that anyone from 0 to 16 would be mapped with 0, child, 16 to 26, young, and then 26 to 36, adult, 36 to 62, middle age, and anyone above 62 would be senior. Okay. So I take the age criteria and pass it through this ranges and populating it with these values. And after doing that, go ahead. We have taken age and we have simplified age a little bit. After simplifying age, now this has become a categorical feature. Once it's a categorical feature, I can use bar chart. And looking at the bar chart, we observe that okay, maybe it has some value. Okay, people within age groups of so let me back. Okay, zero is our child category, and we see child category uh, survived more, died less, or little difference. Then we have young category 1, which is orange. Young category died more, survived less. Middle age died more, survived less. Green is probably your okay. Middle age, okay, 2 was adult. Middle age, again, this is green. And then finally 4, old, definitely died, did not survive as much. So it gives us some idea. Again, as I said, it may be difficult for us to see how this may value the classification task, but hopefully the machine learning algorithm can see through high dimensions and may use this to filter out some more data. Okay. So that is our that is our age so far. Once we look at the next sum, we see embarked. So within the trained data set, there are no embarked missing values. Let me run this again. Actually, I have to run this in order. Within train, there are two missing values for embarked. We'll try to fill this missing values now. So here, what I do is I create a stacked bar chart, but instead of having survived and dead on the x-axis, we have first class, second class, and third class on the x-axis, and the bar represents where did the people embark from. So class 1 embarked from S and C. Class 2 embarked from all three places, very less from Q, and class 3 embarked from these categories. In either of the cases, we see that in either class 1, 2, or 3, more than 50% of the people embarked from S. And now we have just two missing values. What we would do is we would say that, okay, fill the missing value with S. Only two values would not make a lot of difference. And we see that most of the people have embarked from S. I think S is Southampton. So we will say that for the missing values of embarked, let us populate that with Southampton. It's a very simple, small decision. Going ahead, we say again S, C, and Q, even though they are single strings, we cannot pass it to the algorithm. Let us replace them with 0, 1, and 2. So again, we go to the step of title mapping 0, 1, and 2, and we would have at this point, I do a train head. We can see our embarked has become numbers now. Okay. Finally, we look at fair, and do we have missing values for fair? Check. So we don't have missing values for fair in the train. What about test? So we get test dot is null dot sum. Okay, we have one missing value for test within for fair in test. So we said, okay, let us fill the missing value of fair. So instead of just blindly filling the median value, we could say that go to the passenger class, and for that group of passenger class, for that fare, give the center value. Because passenger class adds some extra information. We know that passenger class also meant how costly or how cheap the ticket would be, and we use that information to populate the fare. Let's go ahead. Again, when we look at fare and we plot it using this kdeplot, we can see that maybe individual fares may not matter, and groups of fares would matter more. So looking at this plot, we further said, let us go ahead and again bin this information. So anyone less than fare 17, let's call it 0. 17 to 30, let's call it 1. 30 to 100, call it 2. And greater than 100 would be 3. And with this idea, we could also, group or bin the different fare values. By doing that, we have taken care of this fare part. Let's look at cabin. So cabin, if we do value count on cabin, we can see there are multiple. There are actually 147 different cabin information that we have. A different number of people in that cabin, 4, 4, 3, and so on. We also, after doing that, we say that, okay, let us take the cabin dataset and extract only the first parameter. That is cabin class G, cabin class C, cabin class B, D, and so on. Okay. So instead of taking all of these numbers, which would create so many categories, 147 categories is too much for our model to probably comprehend. Again, that would be confusing the model. So instead, we would say that let us just take the first string, and if we do that, and then for that first string, we look for different passenger classes, that how different passenger classes have been accommodated within those strings. We can probably see here that second class and third class does not have certain colors here. That is, C, it does not have the color blue, it does not have the color orange, and this color violet thing. Okay, so we can probably see that passenger class 1 belonged to or had A, B, C, ABC. Okay, maybe ABC were predominantly boarded with passenger class 1, and uh, D is till class 2. So D is for class 1 and class 2, not class 3, and so on. So we can see that there is some correlation with the cabin title with the passenger class. And we say that, okay, we have different passenger classes here, which goes from A to probably G and even T, and we will replace those with certain numbers. So again, I cannot take A, B, C and pass through the algorithm. They say, let me map A with zeros, B with 0.4, C with 0.8, D with 1.2, and so on. So some association of numerical order for both train and test. And after doing that, we will fill the cabin missing values with the passenger class median value. Okay, so we saw that passenger class has to do something with cabin. Cabin has lot of missing values, but we can use this information of passenger class and then add that and use that information to fill the missing values of cabin as well. So once we do that, we see that, okay, now we have dealt with all missing values for train. I think we would have dealt with all missing values of test as well. Yes, we have dealt with all missing values of train and test. Okay. Now we can go to the next step of seeing if we can combine certain features to get some more information. So instead of having two features, sibling, spouse, or parent, children, I'm creating a new feature called as family size. And to evaluate family size, we're just adding both these values together. And I'm adding +1 representing the person that we are talking about. Okay. If we're talking about Mr. Henry and Mr. Henry has one sibling spouse, then the family size would be 1 + 1, which is 2. So very simple idea of applying family size. So adding this to and then looking at the plot of KD with respect to family size, you can see that within family size, maybe 2 to 4 survived more, other classes not so much. So again, we'll take family size, and family size is a big number going till 11, and all of our other data now, our new data, are smaller numbers. So we map them into a small category, say, okay, from family mapping of 1, we put 0, 2, 0.4, 3.8, and so on. So that by 11, we have a family size of just 4. So what I'm doing is I'm also doing something called as normalization, but I'm not doing it automatically. I'm doing it manually. I'm setting the ranges of the different numbers, ranges of the different categories within similar numbers, so that again, we would not have to look into normalization so much. After applying that on train and test, we can see now we have a new feature called as family size. Since we have a new feature of family size, we can actually go ahead and remove certain information. So we see that ticket is no longer important. Ticket, we are not extracting any information at this point. So sibling, spouse, parent, children, ticket, we can simply drop. After running through this, we drop those values. And even survived category, to make train and test similar, I'm extracting survived into a different variable. So here, target variable, we are extracting survived into target. And after doing that, we can go ahead, look at train data. We have also removed passenger ID. Again, passenger ID would not be meaningful to our model. It is only meaningful while submitting the data. Passenger ID would be important. So at this point, we can simply drop passenger ID, and this is what we are left with. Okay, after doing all of this mess, we are left with this is the train data.head. Let me also see. test.head, and now we have a neat format. So within test, passenger ID I have not removed. I don't know why. Okay, but hopefully you're getting the pulse of what we're trying to do, right? We are trying to take all of our data and make it cleaner, make it a small set that we can feed to the model, which will be able to take all of this information. So now we have only 8 features: 1, 2, 3, 4, 5, 6, 7, 8. Only 8 features, 8 numerical features within probably similar ranges that can help us to train our model. So now if we do train data dot describe, we can see that 1, 2, 3, 4, 5, 6, 7, 8. For all the 8 features, we have some values. So we have mean, standard deviation, minimum, maximum, and so on. And the next step would be to learn some machine learning algorithms and feed this data to those algorithms to see what output it can give to us. Okay. Now, this was probably our major task so far. So as we said, when I was talking about data preprocessing, I said that we spent around 80% of the time, even in some projects, it could be even 90% of the time doing these steps. So these are very menial tasks, very small tasks, but they are very important to clean out the garbage from our dirty data so that we can feed clean data to our model and thereby get some meaningful results. Okay. Do you have any questions? No. Okay. Great. So the next, maybe we'll not continue next. Now we'll probably end it here. You can go through this data. Here I start with modeling, but before modeling, I need to go back and talk about what are the different machine learning methods. Next class we will start with supervised classification methods, which can further help us into see how algorithms are made, what is the theory behind them, what is how do we evaluate if algorithms are doing well or not, and we'll explore some basic ideas of commonly known machine learning algorithms. Yeah, if you have any questions, we can discuss that. Otherwise, we'll stop for today. Okay.
Actually, I'm good.
Okay.
Not
Okay. Great. So I'll stop sharing and I'll stop recording.